All right, welcome back to Remote Monday. We are on section 1-2 now of line segments and distance. So again, vocabulary, examples, and from there we'll do some that you try. Again, there is a lot of vocabulary. The book gives you more than what I'm going to probably give you, but we'll be all right. So I mentioned several times last week that there is a difference between what a line is and what a line segment is. So a line goes on infinitely in either direction. Whereas a line segment ends at a point on both ends. So if I was to draw a line segment, it would look similar to a drawing like this, where I have a point there at both my ends, whereas a line itself has my arrows to denote it's going on infinitely. If I am writing line segment AB, remember that I need to draw those arrows above AB, so I know that I'm talking about a line specifically. Whereas if I'm talking about a line segment, I'm just going to draw a line over top of them without any arrows to denote that I'm talking about a segment with the endpoints, so a line segment, versus an actual line. So something else that you need to know is what's called the betweenness of points. So that is where it is the between the points. It's very self-explanatory, so I'm not actually going to write that one down. So if I was to give you a model though, so if I give you a picture and it looks like this, so this is going to be an example. You're going to have point P and you're going to have Q with M someplace in the middle here. So I have a line segment from P to M. So this is PM. Oops. Should probably write a P instead of a B. So this is PM, and this is a line segment. And then you have MQ here. So there are two line segments so far, and then I have a third line segment from P to Q. So I have three line segments. Notice each of those places are abruptly ending with points. But I also have one line. And I could name that line with anything that I wanted to, any of those points, as long as I draw those with arrows over top of it. So something else that we could say is that the distance of PM plus the distance of MQ, so plus line MQ, is equal to line segment PQ. And we're going to get into distance here in just a second, but that's just an idea of what we're going to be getting into. So to give you an example of getting into that distance idea, I'm going to give you the line. This will be example 1. I'm going to give you the line. I'm going to have the point E, the point F, and the point G here. And I'm going to tell you that this distance from G to F is 2 3/4. We're very seldom going to use mixed fractions, but for right now we're just going to leave it 2 3/4. And I want to know EF plus FG, and both of those are segments, is equal to EG. Basically, we're just proving that this is true. I'm proving what this is. So this term here, what that is set up as, is known as this betweenness of points. That is the theorem or the axiom that we're going with. So it's called betweenness. Of points. But something that we need to know is that we're going back to when we talked about those order of operations and expressions and plugging in numbers, because I know that EF is 2 3/4. And I know that FG is 2 3/4. So again, I'm plugging in that information that I know, which is why it was important that I think 2 weeks ago now, we went over plugging in numbers and solving for equations and expressions. So that is known as our substitution. We've plugged in those numbers that we know. And then we're just going to add them together. When you add them together, you get 5 1/2. And I should have marked that these were inches. You'll have some kind of value or unit that they are. Is equal to 5 is equal to segment EG. So that's all that is. That's all that we're doing with this particular problem. So I'm going to give you one like this at the end, but that was example number 1. So sometimes, though, maybe you're given some stuff with variables in it. So example number 2, you're going to have your line segment. And Y, Z, and X. And this distance that I'm going to give you is 5a minus 4. 3a is here, and 14 is here. So you're going to use what we know. We know that the distance of xy plus the distance of yz. So I take each of those separate segments. So xy, oops, I thought I clicked my highlighter. xy plus yz gives me my full segment. So I use that betweenness of points idea, and I know that that answer is going to give me xz as a whole. And I write a line in my z so that way it doesn't look too much like a 2. So now again, I'm going to use substitution. I know that xy is that 3a. And I know yz is 14. And I know xz is 5a minus 4. So here again, you're just solving for a. You're going to find what that a value is equal to when we solve. So we want to get our a values on the same side, numbers on the other. You can do that in any order that you want to. I'm going to cut to the chase here. I'm going to do it all in one step. 2a, divide both sides by -2, and you'll have that a is equal to 9. So a is equal to 9. Again, you'll want to check your work. I'll give you an example of that in a moment. So hopefully those two made a little bit of sense. We'll see how you do when you get your own. All right, so some more vocabulary. If two figures, so the word congruent, and I'm sorry, you're going to have to listen to that because I can't block out the noise. So if two geometric figures have exactly the same shape and size, so they have the same shape and size, then they're considered congruent. So we're also going to be talking about transformation later on in the pre-image before that, so we'll get there. Those are some other words that are kind of italicized in the book. There's also this term of rigid transformation, and that's a transformation where the position of an image is different, but the two figures are essentially the same. We'll talk about all of that when we get back to transformations, but we're not quite there yet. So then there's also congruent segments. And congruent segments is when there are two segments, but they are in different locations. Oops, I shouldn't have put my dots there. There we go. Okay, so go. Two segments that are equivalent but in two locations. So that's all that a congruent line segment is. They must have the same measure. That's what it means to be equivalent. All right, so some ways that we're going to be denoting these congruencies. So if I have line segment AB, and I'm not perfect, so bear with me, and I'm told that it's 1.7 centimeters, but then I also have line segment CD, and I'm told that it is 1.7 centimeters, I know that they are congruent, and that's what that little line is that I just drew, that changing it to blue so you can see that I did something. So that line there is just saying that those two things are congruent. That is how it would be if I'm drawing a picture. I could also say, if I'm writing a proof, which we'll get to later in the year, I'll also say that AB, so that line segment of AB, is congruent, which is that fancy symbol there. That fancy symbol means congruent, to CD. And we'll work with congruency throughout the week. And we'll also be working with what's called a construction and actually taking a line segment and then moving it to another surface. So finally, we have distance. And distance is the length between two points on a line. I totally just forgot how to spell length when I did that. There we go. Length of a segment between 2 points. So if I'm looking at my segment here and I'm given the segment P and the segment Q, and I'm given probably a location of these things, so this might be x1 and this is going to be x2. The distance is equal to the absolute value of x2 minus x1. So if I'm told that this is 0.5 and this is 0.3, I would do 3 minus 5 and take the absolute value of it to find what that distance is. So for a more numerical example, if I'm giving you a number line and I have 5, 4, 3, 2, 1, 0, negative 1, 2, 3, 5, 6. And I have a point F on 5, E on 2, D on negative 2, C on negative 4, and B on 6. And I was to ask you, what is the distance? This is example 3 of the segment BE. Well, I'm going to find what let me find a highlighter, coordinate value is for B and what my coordinate value is for E. Oops. And then I am going to, from there, take my, I need a pen, take my x2 value minus my x1 value. So it doesn't matter which one's x1 or which one's x2. So I'll say x1, x2. So I'm going to have 2 minus, because I have to bring that minus sign down. And then I'm told that my other x value is negative 6. So I labeled E as x2 and b as x1. I'm just substituting in. And then I'm going to solve. So if I have a minus and then a negative, I'm really adding. So I've got 2 plus 6, so the absolute value of 8. And remember, when we take the absolute value of anything, it's always positive. So the distance of BE is equal to 8. So we also might sometimes use these to say, okay, are two segments congruent to each other? So maybe I say, is CA and ED congruent? So you'd have to solve for the measure of CA and the measure of ED. And if they're the same, then yes, they would be congruent. And if they're different, they wouldn't be congruent, because remember, congruent line segments have the same measure. So I'm going to go ahead, I'm going to give you 3 problems for the U-Try. Use your notes to help you out. So problem number 1 is going to be, let's see here, I'll have you give you a line segment. And B is here, A and C. AC is going to be 4x minus 12. AB will be x, and BC is going to be 2x plus 3. So that's the first one that you're going to want to try. Remember, I'll give you this hint. You want to do AB plus BC is equal to AC, and you're going to substitute your values in, combine like terms, and keep going from there. The second one I'm going to give you is going to be the line segments P, Q, R. I'm going to tell you that this distance is 13, and this distance is 6. And I'm going to leave this other distance blank. So I need you to find the length of QR. And then last but not least, if you use that line segment again, your number 3, sorry about that, I keep bumping it. Your number 3 question is going to be RCE and EF congruent. And then finally, in this one, you'll solve for CE, and you'll solve for EF, and there would be congruent if they're equal to each other. So that's what you're trying to find there. So sometimes I'm also going to give you pairs of points and find their congruency. So I'm going to talk about this one, but I don't want you to, I'm not going to give you anything to actually solve. We'll work with this more in class. So those are the 3 questions I'm looking for. And the last thing that I'm going to be doing in class is I might be giving you 2 coordinate sets of C being -4, -6, and D being 5 and -1. And there is a distance formula which you're going to want to know. And that distance formula is x2 minus x1 squared plus y2 minus y1 squared. So if I just give you these 2 coordinates, what I'm doing is I'm going to maybe say this is x1, y1, x2, y2, and I'm just going to plug them in to my equation here, and then I'm going to solve for it. So if I was to plug it in, I would have my equation here. I'm going to have my square root. My x2 is 5 minus my y1, which is -4. Square all of that. And then my y2, which is -1, minus my y1, which is -6. So I'm just plugging in the numbers that I know. Once I do that, I actually perform the operations, just like we do with order of operations. So 5 minus -4 is really 5 plus 4, which is 9, plus -1 minus -6. And if I'm subtracting a negative, remember I'm really adding, so I have 5. From there, I would do 9 squared, which is 81, plus 5 squared, which is 25. Add those together, and that gives me the square root of 106. And I can't simplify that square root, so I'm just going to leave it. So we will be doing things like that in class as well. Again, I'm not going to give you a problem on that to solve, but there is one last question for you to finish, and then you're good to go. Ah.